Hello, I'm audible to you? And the screen is visible?
Yes, sir.
Okay, fine.
Sir, I have one doubt.
Yeah, tell me.
इंटीग्रेशन z प्लस वन अपॉन जेड स्क्वायर प्लस वन है तो उसमें और सर्कल दिया है मोड z इक्वल टू वन.
Okay.
तो ये जो i और माइनस आई है ना नीचे डिनोमिनेटर में z स्क्वायर प्लस वन, सो वी टेक z प्लस आई z माइनस आई.
Yeah, fine.
उसके पार्शियल फ्रैक्शंस लेने के बाद
Yeah.
कैसे उसको कैलकुलेट करना है? मींस ये आई और माइनस आई दोनों सर्कल पे है पॉइंट.
Okay, so you want to calculate the integral z plus 1 upon 1 plus z square on the
Yes.
unit circle.
हाँ, yes sir.
Okay, so basically like in the definition of integral we have mentioned that function has to be continuous on the curve, isn't it?
हाँ.
Yeah, so here your function is not continuous on the curve.
Yes, हाँ.
Yeah, so basically you cannot do these kind of things. Okay.
But function is not continuous at 2 point ना sir, I and minus I.
Yeah, basically see to define the integral we have previously we have posed a condition that f has to be continuous on the curve. Okay, so like in physics in some application part what we do, we choose, suppose that I and minus I, we choose some neighborhood, okay, like a circle kind of thing, okay, and we make you take a upper half circle and lower half circle, okay.
Okay.
Now you calculate the integral on that one, because upper half circle and lower half circle that function is continuous, there is no problem, isn't it?
हाँ, okay sir.
Yeah, or right half circle, since you are saying I and minus I, so you take right part of circle and left part of the circle, okay.
Okay.
So on that function is continuous, okay. So what you can do, you can calculate the integral on that one and you take epsilon tends to 0, okay.
Epsilon tends to 0. हाँ, yes.
Yeah, so basically whatever the integral you will see in this complex analysis class, whatever it is, so the function will be continuous on the curve, okay.
Okay.
It can have singularities inside of the curve but not on the curves, okay. Function has to be continuous on the curves, okay.
हाँ.
But the question you are asking, it is some kind of the generalization of the integral, okay. If
Yes.
what if the function have discontinuity, like finite at finite points it have a discontinuity, okay.
Yes, हाँ.
So in that case we have to define integral in some different sense,
Okay.
yeah. So I will talk about this in the meeting. So hello everyone, good evening to all. My name is Abhishek Pandey. I am a Prime Minister Research Fellow in the discipline of Mathematics at IIT Bhubaneswar. Today we are going to discuss about week 6 assignment, okay. So let us start. So first we will just recall some basic definitions like homotopy and simply connected domain, okay. So this is visible to everyone.
Yes sir, visible.
Okay. So let gamma naught and gamma 1 be two rectifiable curves in a domain omega, okay. So we will define the homotopy of the curves. Okay. So basically, roughly speaking, homotopy means you can continuously deform a curve into some another curve. Okay. So as a closed curves. Okay. So suppose gamma naught is a closed curve at z naught. So basically, you have a point z naught. Okay. And gamma is any closed curve. Okay. And gamma 1 is a closed curve at z1. Okay. Hello. Samir, can you unmute yourself? Yeah, thank you. So we say gamma naught is homotopic to gamma 1 as a closed curve in omega. So just remember that this homotopic property also depends upon the domain. Okay. So that's what I'm saying, gamma naught homotopic to gamma 1 in domain omega. Okay. So they are said to be homotopic. If there exists a continuous function, this h 0 cross 0 comma 1 cross a comma b to omega, such that this satisfies these conditions. Okay. So what does this means is, so here you are having, okay, wait, so let me just draw it. So okay, so here you are having 0 and 1, and suppose somewhere a and b, and at z naught you are having a closed curve. Okay, and at z1 you are having some closed curve. Okay. So what this condition means is, so h of 0 comma t basically equals to gamma naught t. Okay. So let us say this is your gamma naught and this is your gamma 1. Okay. So basically h 0 comma t. So 0 comma t basically where t belongs to 0 comma 1. So this should be t. Okay. So where t belongs to 0 comma 1. Okay. So here it should be a to b. Okay. So you fix 0, so you will get this line. Okay. And you will get this line. So this line maps to the gamma naught. Okay. And h of 1 comma t. So basically 1 comma t is here. Okay. So 1 comma t where t belongs to a to b. So this line maps to here. Okay. Now this s comma a. Okay. So basically s comma a basically will here. Okay. So basically s belongs to 0 1. Okay. And s comma b. Okay. This is your s comma b. Okay. Like here s comma like points represented from s comma b will belong here. Okay. So these are equals. Okay. These two are equals. So once you define gamma s like this, h of s comma t. Okay. So gamma s from a b to omega, where gamma s of t is equals to h s comma t. Okay. So you basically you fix s and you vary t. Okay. So basically you will fix x someone here and you vary t. So these will be this, some curves will be there. Okay. This one. So these intermediate curves will map something here. Okay. And something here. Okay. These intermediate curves. Darshana, can you mute yourself? Anything?
Okay.
Yeah. So these intermediate curves will be here. Okay. So basically what you are doing, you are deforming a curve, continuously deforming a curve into some another curve. Okay. So this is the definition of homotopy. So basically this gamma s gives you a continuous family of curves like this one. Okay. Continuous families of curve. Okay. Okay. Yeah, note that there is a remark. So for s 0 to 1, gamma s may not be rectifiable. Okay. But in practice, when gamma naught and gamma 1 are rectifiable and smooth, okay, gamma s will also be rectifiable or smooth. Okay. So just remember this in mind once you prove a theorem regarding this. So this might be your obstacle. Okay, like gamma s may not be rectifiable. Okay, but in practice we assume that these are these are rectifiable when gamma naught and gamma 1 is rectifiable or smooth. Okay. Now fixed endpoint homotopic. So here you are having two curves. Okay. So suppose z0 and z1. These are having the fixed points, like same initial points and same terminal point. Okay. So here you are curve gamma naught. Okay. And here is your curve, suppose gamma 1. Okay. So these are said to be homotopic if the same thing is there. Okay. Same continuous function should exist. Just this condition changed to z0 and this condition changed to z1. Okay. So in either the case, this function is called the homotopy from gamma naught to gamma 1, and if gamma naught is homotopic to gamma 1, we denote it like this. Okay. So basically these two are the informations. Okay. So let this C omega denote the set of all closed rectifiable curves in a domain. Then this defines homotopy. Homotopy defines an equivalence relation on this class. Okay. And similarly, you fix 2 points and collect all the rectifiable curves which joins z0 and z1. Then FEP homotopic. FEP means fixed endpoint points. Okay. Fixed endpoint homotopic. So FEP homotopic defines an equivalence relation on this one. Okay. So null homotopic. So a curve, a closed rectifiable curve in a domain omega, we say gamma is homotopic to 0 or also called null homotopic if gamma is homotopic to a constant curve in omega. Okay. So just remember this in mind. So I will just quickly recall the Cauchy's theorem homotopic version. Okay. So let omega be a domain and f omega to C is holomorphic. Okay. So omega is any domain and f is any holomorphic function on this domain omega. Okay. So this is the version 1. If gamma naught and gamma 1 are two closed rectifiable curves in omega and gamma naught is homotopic to gamma 1, then this holds. Basically the integral is same. Okay. And if gamma naught and gamma 1 are two rectifiable curves in omega from z0 to z2, okay. So this is your gamma 1 and this is your gamma 2, this is your z0 and z1, okay. And gamma naught and gamma 1 are fixed endpoints homotopic in omega, then these integrals are same, these two integrals are same. Okay. Now version 2 is basically, so so suppose you have a closed rectifiable curve in omega such that gamma is homotopic to a constant curve. So such thing is known as homotopic to 0. So if gamma is homotopic to a constant curve, this integral will be . So this integral will be 0. Now let us see the definition of simply connected domain. So a domain omega is said to be simply connected if every closed rectifiable curve in omega is homotopic to a constant curve. Okay. Now let us move towards the assignment. First question. So it is asking which of the following statements are true. So first question is, if gamma 1 is the unit circle centered at 10 and gamma 2 is the unit circle centered at 0, then gamma 1 gamma 2 are homotopic in C. Remember that homotopic also depends upon the domain. Okay. So here this is the gamma 1, okay. This is your gamma 1 and this is your gamma 2. So basically we have to show that whether this is homotopic or not. So for the homotopic, this define this as the function, okay. So this is called the linear homotopic, okay. So 1 minus s gamma 1 t plus s gamma 2 t, okay. So as you can see that these all the conditions of homotopy holds, and since also HST is continuous, thus gamma 1 and gamma 2 are homotopic in C, okay. Now if second option is if gamma is a curve in omega, then gamma plus minus gamma is null homotopic, okay. So basically this is your curve, okay. So this is your curve gamma, and minus gamma will be just trace it back, okay. So basically as you can intuitively you can say that this is going to homotopic to Z naught, okay. So this gamma plus minus gamma is homotopic to Z naught, where the curve gamma starts, okay. Now let us look at the third option. If omega is an open connected set and gamma 1 and gamma 2 are two curves which are homotopic in omega, then gamma and gamma 2 are homotopic in any open subset contained in omega, okay, which also contains the image of gamma 1 gamma 2. So this is not true. We will see this one. So basically let gamma 1 be the unit circle center at 0 and gamma 2 is the unit circle center at 10, okay. So we know that gamma 1 is homotopic to gamma 2 in C, but gamma 1 is not homotopic to gamma 2 in C minus 0, that is punctured plane, okay. So this option is not true. Similarly, last option is basically if gamma 1 is homotopic to suppose a curve sigma 1 and gamma 2 is homotopic to a curve sigma 2, then gamma 1 plus gamma 2 is homotopic to sigma 1 plus sigma 2. So this is also true, okay. Let us move towards the second question, okay. So the first question is the first option is if gamma is a closed curve in omega and if f is a holomorphic function on omega, then this integral is 0, okay. This we need to check, okay. So let gamma t is a unit circle, okay, and omega this domain. So omega is basically a disk of radius 2 which is punctured at origin, okay, and take the function 1 by z. Clearly f is holomorphic on omega, but the integral of f over gamma is non-zero, okay. So this option is not true. Now the second option, as I already mentioned, if gamma 1 is the unit circle centered at 10 and gamma 2 is the unit circle centered at 0, then they are not homotopic in C minus 0, okay. This you can see. So suppose they are homotopic, okay. So take the domain C minus 0 and function is this. So if they are homotopic, by Cauchy's theorem integral should be same. This is the integral, but as we know this is 2 pi I over the circle gamma 2, but this is 0, okay. So this is also not correct, okay. So this is correct, are not homotopic, okay. Let f be a given holomorphic function omega, and if gamma is a curve such that this integral is 0, then gamma is null homotopic, okay. So this is also not true. We will see this one. So basically you consider the domain disk of radius 2 which is punctured at origin, and you take the unit circle again, then clearly fz equals to 1 by z square is holomorphic on this one. But as we know, integral of 1 by z square over the unit circle is 0, but gamma is not null homotopic in omega, okay. So this option is also not true. Now the fourth option is if f is holomorphic function on omega and if omega is a curve which is null homotopic in omega, then basically integral of f is 0. This we need to check, okay. So basically f is holomorphic. So basically f is holomorphic and gamma 1 is null homotopic in omega, that is gamma is homotopic to a constant curve omega in gamma in omega. So this integral will be same, and this is the integration over the constant curve of a holomorphic function. So this will be 0. Okay. Now let us look at the last option. So if gamma 1 and gamma 2 are homotopic curves with fixed endpoints and f is holomorphic, then this will be equal. Okay. So basically if gamma and gamma 2 are homotopic curves, so basically so gamma naught plus minus gamma 1. Okay. So gamma naught plus minus gamma 1, this will be homotopic to gamma 2, where gamma 2 is basically a constant curve at z naught.